Okay, for number 7, we've got this capacitor here with two parallel plates separated by a distance, and they give us that, and they give us the area too. And then the space between the plates is filled with 3 different dielectrics with different dielectric constants, and each one fills exactly 1/3 of the volume. What's the capacitance? Okay, weirdo problem, right? However, this is actually not very hard to solve because what's going to happen here is you can think of this. First of all, let me draw our little capacitor here, or our big capacitor really. And then we've got 3 different areas with, let me draw, I'll use brown for borders there. Okay. And we've got 3 capacitors with, we'll go with red, green, blue. So kappa 1, oh, I'm way too in love with these colors. Okay, kappa 2, and blue is kappa 3. Okay, so here's the deal. When you charge this capacitor up, I mean, the whole point of the capacitor is to charge it up and store charge on it, right? So when you charge this capacitor up, what's actually going to happen is you're going to have a voltage difference, of course. You apply a voltage difference. And, okay, maybe now I'm just being too picky. And let's see. Okay, so let's have the top be the higher voltage. So you apply this voltage V, and what that means is the top plate is at, V volts, or a voltage V higher than the bottom plate, right? And the thing is that the expression, so we have this expression that the magnitude of the electric field inside the capacitor must be equal to the voltage change divided by the thickness of the capacitor, okay? So D is as usual, your thickness there. And this can't change. Dielectric won't change that, even if it switches from one dielectric to another. So we're going to have 3 capacitors, or not 3 capacitors. Well, it is, but we're going to have 3 different regions. But in each of these regions, you have to have the same electric field, which means you have to have the same. You're still going to have these horizontal voltage equipotential curves. So the idea I'm trying to get across here is you still have this uniform electric field here, and so that is not going to change. I'm trying to draw these electric field arrows in blue. That is not going to change based on the dielectric. What the dielectric does change is this expression, which I think goes like electric field must be, let's see, it's going to be the charge density on the plate divided by, no, not divided by 2, divided by kappa epsilon naught. That sounds right to me. Okay, so what's going to happen? Whoops, sorry. What's going to happen here? There we go. Is the dielectrics don't change this equation. They do change this equation. And if they're going to change, since the dielectric constant changes this, if all 3 spots have the same electric field, so you got the same electric field magnitude through all 3, okay? Because this is inviolate, okay? This does not change. So you have to have the same electric field, which means that if these 3 regions here, 1, 2, 3, have different values of kappa, the capacitor is going to adjust by distributing more charge to some of them and less to others, so that if the one that has the highest kappa will have the greatest charge density. So what's going to happen, and I think the order on these, let's see, K1 is 8, K2 is 10, and K3 is 12. So let me just write those in. Okay, and I'll do them all in red. Or not K1, sorry, it's kappa 1 is 8.0, kappa 2 is 10.0, and kappa 3 is 12.0. And so what you're going to get is that since this guy here has the lowest kappa value, he's also going to have the lowest charge density. This guy here is going to have a higher charge density, and this guy here, number 3, with the highest kappa, must also have the highest charge density, because they're all going to have the same electric field magnitude in all 3. So there are a couple ways around this. One way is to break it up into 3 different capacitors, okay, each with the same plate area and same distance, or same D, same plate separation. So for all 3 of these, same A and D, and then this guy has kappa 3, this guy's kappa 2, this guy was kappa 1. Okay, so 3 in parallel, and that'll work just fine. That's probably the easiest way to do it, and just find the charge on each of these, or the capacitance of each of these, and add them up for parallel. So why not do that? So each of these has the same area, but the area of each of these is the A they gave us, which is 18 square centimeters, right? And that divided by 3. So I'm going to keep A equal to 18 square centimeters, which is, now this is tricky converting it to square meters, because it's not 0.18 square meters. You don't just shift it 2. You've got centimeters squared, so you have to shift it 4 digits. So 0018 square meters. Okay? And if that's a little confusing, think about how many square centimeters there are in a square meter. Not 100. There's 10,000. 100 times 100. Okay? So there you go. Anyway, so then I'm going to say each of these has area of A over 3. Do-do, do-do, and do-do. And then, of course, they all have a separation of D. Okay? So this guy I'm going to call capacitor 1. This is the region with, kappa 1. So C1 is going to be, well, let me just write out my parallel plate equation here. C equals A epsilon naught over D, except, well, see, I forgot already. I've got that whole kappa thing to deal with, so I wish I could do this on the marker board. Okay, so C equals kappa times A epsilon naught over D, which means for 1, I mean, this is pretty obvious, right? So capacitance for 1 is, C1 is kappa 1, kappa 1, and then the area of this capacitor is A over 3, right? So this is going to be kappa 1 A epsilon naught over 3D. And then similarly for 2 and 3. I'm not going to do all 3 of them because I think you see what's going on here. But let me scroll this down. When we have, these are 3 capacitors in parallel, right? And when we have capacitors in parallel, the rule is that you add the capacitances up. Okay, so the overall capacitance is capacitance of 1 plus capacitance of 2 plus capacitance of 3. Okay, and so you can see now this guy has a capacitance of kappa 1 A epsilon naught over 3D. And so this guy is going to have the same, except it's going to be kappa 2 in place. So what you're really going to have, when you sum all these 3 up, I'm just going to skip a step ahead, you're going to have kappa 1 plus kappa 2 plus kappa 3 times A epsilon naught over 3D. Okay, so at this point, really, it's just plug and chug. I guess, let's see, so what do I want to do? This is 8, let's see, okay, 8 plus 10 plus 12, this is going to be 30.0, all this stuff in here, and then our area, we said, was 0.0018 square meters, so 0.0018, it's off the screen now, but trust me, okay, epsilon naught, oops, I don't want to write that in, is 8.85 times 10 to the minus 12, and numbers that are incredibly useful in everyday life. And then 3 and D is 1.20 millimeters. So we have our 3 down there, and D is 0.0012 meters. Okay, and so now that is everything we need. Really what it's going to end up being is, let's see, so we can do this pretty fast. This will be, turn this into 10 and get rid of this, and then 0.0018 divided by 0.0012 is 1.5. So this is going to be 15 times 8.85 times 10 to the minus 12, and la 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 la. Okay, so 8.85 times 15, that gets us, 8.85 times 15 is 132.75. So really what we're going to do is just shift things 2 digits. So we got 1.32. Alright, I guess that's right. So this is going to be come on. Okay, I don't know why I'm getting those circles. Okay, 1.32 times 10 to the minus 10 farads, which is 132 picofarads, which is really tiny, but I guess, I don't know, I suppose it's not a very big plate, and that's kind of a wide distance, so maybe that's par for the course. But anyway, that's... Did I do that right? Yeah, I did everything. Okay. So, there you go. That's how you do number 7. I assume that's correct. If not, I'm sure I'll hear from people.